Yep, so thanks everyone for joining. So my colleague Mustafa and I will be presenting how to improve your search engine results using large language models. So Mustafa and I are both machine learning engineers for Walmart, an e-commerce site in the United States. So this is the link to the GitHub repo. So if you want to follow along with the notebooks or um, yeah, and we also have a link to a PDF version of the slides. Um, yeah, at the root of the repo. We'll go through some of the setup. There may be some issues with setting up the notebook completely. So during the session, we wanted to cover a lot of material, so we may not be able to run all the notebooks live, but we'll look at some of the rendered output. Yeah, so this is the link. I shared it also in the resources, but it's just this user ID, and this is the repo. So who's the audience for today? The audience who members who will gain the most values are if you consider yourself like a beginner in the large language model space, if you're a beginner in the search space, so if you don't have any prior knowledge. If you're looking for how to actually apply LLMs in a uh, in a practical use case, if you're already familiar with libraries like LangChain, RAG, and if you've already fine-tuned your own LLMs, you may not get much value from this session. But hopefully, there's still some new things that you might learn. So I would say this session has about maybe 5 sections. So after most of those sections, there is like a small Jupyter notebook. Um, so we'll be running it inside our environment, but it may not completely run in Colab. So definitely do feel free to run it locally or in Colab externally. But we'll just be going through the notebook slide. So yeah, so there's about 5 sections here. We'll introduce the space of what are the problems with e-commerce search. How can just like a very brief rushed overview of large language models for someone who might be new to the space, um, and how you can use something like prompting to talk to your large language model, and how can you fine tune your own large language model. And then we'll close the section with kind of seeing about how other companies in the e-commerce space are using LLMs. Um, Again, after each section, there's like a notebook that we'll be going over. And after each section, we'll also pause for any questions. Um, so again, we hope the takeaway that you have from this section is, understand the e-commerce space, what are like the NLP problems that exist there, how you can use LLMs to solve some of those problems, like a practical application of how you can use like a library like LangChain to talk to some of these LLM providers, and the results of like a pre-trained LLM versus something that's fine-tuned for your own use case. So let's get started on the intro. So I would say like in an e-commerce search space, there may be 4 problems, and I have a diagram that kind of illustrates these problems. So let's just go to these problems directly. So the first thing I would say is like understanding the intent of a user's query. Let's say you go to Amazon or Walmart or whatever e-commerce retailer, and you type something like red Nike men's shoes 10 inches. Like you want like the backend or the vendor to basically understand that this user is talking about these certain type of attributes. That they're looking for shoes, and they're looking for shoes. The shoes has to have the color red, the brand has to be Nike, and the size has to be 10 inches. So that's one side, understanding the intent from the query side. You have the same happening on the item side. You may use the same models that you have been using on the query side, or you may build custom models that might be running on the item side. So now that you have you understand the intents of the query and the item side, now you need to figure out is this item relevant for the query? So for this query, red Nike men's shoes, like the first shoes over there, it is red and it is shoes, but it's not for the male gender. So that's obvious that this item is definitely not relevant. The second image here, there's some green, but I would say mainly the shoes is kind of on the red color. So this item is relevant. The socks, the socks item, it matches 3 of the 4 intent of the user, but the product type is not socks. What about the last item, right? So it is red, it is male, it is shoes, but the brand is not Nike. Is that an issue? Maybe the user explicitly asked for Nike, so they do want Nike shoes. What happens if the shoes was like 11 inches, but it was a Nike shoes? Is that relevant or not? So depending on the context, even if some of the attributes match, the item may not be considered relevant. So we covered query understanding, item understanding, query item relevance. And the last problem that I would say that we would kind of cover about is queries with ambiguous intents. So, you as a user, if you go to Amazon and you see Christmas gift ideas, when you search for a query as ambiguous as this, you're also looking for inspiration or gift ideas, right? So in order to kind of make sure these items match to the query, these merchants who upload their items on these e-commerce sites, they kind of stuff the title, right? So you see this rose, the first image of a butterfly and a rose in a cage, um, like there's so many tokens or so many terms in the title, right? It's for women, mom, Christmas, birthday gifts, grandma, everything is put there, right? And I find the second example a little bit interesting too. This is a non-stick skillet, but if you look at all the way at the end of this, it says ideal Christmas gift. I don't know. I mean, I'm surprised to learn a skillet is a good Christmas gift, but the seller of this item wants to make sure it matches for this query, so they decided to add that term at the end of the title on the Amazon listing. Here's another example of I would say an ambiguous intent. So zero waste oral care, right? So here, what is the user searching for? Are they searching for toothbrushes? Are they looking for zero waste toothpaste tablets? Or are they looking for floss? So this again another example where if you just go with matching the tokens that may be in the query and the item title, you may not come up with a good enough approach. So just reiterating the 4 problems that we talked about. So the first one is understanding the intent of a user's query, understanding the intent of an item, understanding if a query and item pair is relevant, and for cases where you have an ambiguous queries or the item title suffers from a lot of title stuffing, how can you match those intents? So we know the problems, and they're pretty advanced and rich systems there. But let's take a very naive approach for solving this problem. So let's say this is not an e-commerce query, but let's take this query here of like pictures of kitten playing, right? So there's normally a flow that goes when this query is processed. The query might come into your system like as a string, but you might decide to split the tokens by white space. Afterwards, you see like some terms like the word off, because it's kind of like a common term, you might remove them, right? Then the next thing you might do is like, there's the word playing, it becomes play, right? So you remove the suffixes, right? You might stem the words, right? So this 4-token query now is like a 3-token query, and it kind of is a little bit different from before. Playing became play, and then you search your catalog for which items might contain that token. So the first document or first item has the word playing, so it kind of matches with play. The second document has the word kitten, so that kind of matches. Document 3, it technically has all the terms, but the document is longer. It's not talking about just kittens. It's the kitten is not playing, the kitten is sleeping, it's a dog who's playing. So it technically contains all the tokens, but is it really relevant to the query? So yeah. So the data set that we'll be going over in today's section is like an actual e-commerce shopping data set that's provided by Amazon. So yeah, let's kind of get started here. So as I mentioned, like before the lab, we did notice some issues with Colab. So we'll go over the notebooks again, and like we'll run it live, but you may face some issues. So um, so in the notebook here, like we do have the binder link, and so if you click on it, you will be taken to an environment. But just in the interest of time, cover materials, like we'll be running it from in one of our environments, just to kind of show the materials, but we will be running it live. Yeah, so let me run this notebook. So at the root of the repo, uh, this is the repo that kind of sets up things. So we just clone the repo. Inside the repo, we have some requirements. We'll go over like some of the core packages that we're using, but it's mainly like using LangChain, and LangChain can support talking to other LLMs, so it's just some other dependencies there required for that. And we'll be installing like Elasticsearch. So Elasticsearch is search engine system that it's open source that allows you to kind of build like a simple, full text search engine system. So we'll look at the results of that. So in Colab, if you want to set Elasticsearch, this is how you might do this, and this is how you might start Elasticsearch in the background. So in our environment here, oops, sorry, it looks like I didn't start Elasticsearch. So maybe let me do this now itself. So we have already dependencies, so let me start. So Elasticsearch can take some time to start. So that's why we just have like a time block of 60, just waiting for a minute. And so just to kind of speed up some things, like we provided like our clean version of the data set. So if you go into notebooks, you'll see like the notebooks with 0 are like some of the pre-processing that we did on the data set, just in the interest of time. Um, yeah. So, but for most of the notebooks, we'll be looking at this cleaned input.parquet. So yeah, maybe while this is running, let me briefly show, let's look at what the data might look like. So, um, so as you know, as you might think, like in an e-commerce data set, we have queries and items, right? Um, so here you have like this query, like a privacy fence. This is the product ID, so the ID that Amazon uses to uniquely identify an item in their catalog. So how do you know if a query and item is relevant? In this case, Amazon sent these query and item pairs to their human annotators to see if the item is relevant or not. So how can an item be considered relevant? Like the human reviewer would look at the query, would look at the item title, and then make that judgment call here. A item can have a lot of metadata. Amazon only provides like the brand and the product color as the metadata. Yeah. So let's see if Elasticsearch is. So Elasticsearch is running. This is just a health check to make sure it's working. So we're just showing Elasticsearch to kind of set like a baseline, like for a simple text-based system. It's not important to understand how things work. Yeah. So Elasticsearch is working. This is, oops, sorry, let me run this notebook again. So this is actually a very rich data set. So Amazon has English queries, Spanish queries, Japanese queries, and they also have like a subset of, their catalog in those regions. So I believe there's like more than 1 million or so query item pairs. So this is the example we saw. For our session today, we'll mainly look at the query, and we'll look at the product title and the relevance label. And to kind of make something. So as I mentioned, this data set is pretty rich. So we do have a lot of human ratings, right, collected for query item pairs. So it's a rich data set if you're interested in e-commerce. So let's look at some of the results that we're getting with a simple baseline. So this is like what, so not baseline. So here we're looking at the ground truth. So in this case, these are results that Amazon's human annotators marked as relevant or not given the query. So this AirPod case cute, unfortunately, Amazon didn't really provide images with this data set, valid images. So not all of them might have images, but let's just click on this item here. So by the rating, it's considered a human annotator found this item as exactly relevant. So I see this is a Apple AirPods carrying case, and I think this is in the color and the material looks kind of nice. So so most of the top items, like they're considered exactly relevant. But if you look at some of these items here, so let me just bring this item here. So this is an AirTag keychain for Apple AirTags. So the user is specifically looking for an AirPod case, but this is more like an accessory for an AirPod. So that's why this item is not considered relevant, or maybe partially relevant, complement in this case. So let's play with some more queries here. So let's look at this Adidas shoes men 15-inch. So the top items that we see here, it's Adidas, it's men's, it's 15-inch. So these items capture the intent of the query correctly. But these items here, the human annotators, because it doesn't have like the exact size match, it's considered irrelevant for them. So yeah. And also let's look at kind of this broad kind of query, like just for men. What is the results that are being returned by the baseline system, and what is the ratings that the human annotators gave? So one of the relevant items is like a Visa gift card, or like a book of jokes, or like a anniversary wallet, like an anniversary card. So the intent that is being extracted from here is like for me, it might not be clear from the tokens itself, but it's mapped to like like a gift card or a a book that's geared for like dads or like father figures or like health equipments or whatnot. So this data set again, as I mentioned, is pretty rich, but we'll just look at these are the examples that we mainly looked at, and we'll look at how our baseline system performs on these queries, and how with like some simple LLMs and prompting, we can kind of improve the results of the baseline. So let me go back to the slides. Um, so, oh, sorry, I showed the e-commerce data set, and I kind of showed the type of queries that are in the data set, but I didn't show like what a simple baseline might actually look. So what we were looking here was the ratings that a human has provided. Let's look at what a simple system that Elasticsearch does. So here with Elasticsearch, we're just kind of matching with the tokens. We're not really doing anything too fancy or not. So, yeah, so the system is running. I'm just going to read the data. So the data set that we have has like query item pairs, but when we index our items, we only care about the item data. We don't care about the query data. So I'm just getting like the product ID, product title, and dropping it. So again, this data set has query, product relevance. We only care about the product details. So today we're just going to be focusing on the product title. So again, the focus of the session is not Elasticsearch. So we just have some wrapper code to kind of hide some of these things. So let's take a look at how a simple token-based system might process this query. So we have, instead of Nike shoes, we have Adidas shoes, men 15. So there are different ways to process a string. So here, we have something called an analyzer stop. So if you know, like in NLP, about like stop words, about removing words that might be appearing too common, or that are kind of very rare. So in this case, like 15 was removed because it's maybe not appearing enough in the corpus, or it's appearing too often. So um, and here's another. This is the default in Elasticsearch, but if you notice, like it does some weird kind of stemming of the terms, like Adidas becomes Adida, which like the brand name is Adidas, so kind of trimming it might not make sense. The processing of shoe kind of makes sense, and this one kind of kept the 15 size token. So so let's look at so this is when you send a request to Elasticsearch for this query, you kind of get an array of documents. You get the array of the relevant document, the score, and the metadata. But this is not really important here. Let's just look at a visual way of seeing these results. So this classic example that we had, or the first example that we looked, AirPod case cute. So so it can happen that like a human annotator might not have had time to kind of review all the possible items in the catalog. For every query, you could possibly be fetching like 1,000 relevant items. So what this is showing here, like in our system, like we are fetching items that that a user might not have rated. So this is an AirPod. It is kind of cute, so it is relevant, but a human annotator didn't have the opportunity to rate it. So it's possible to bring in different items. Let's look at the shoes example from before. So uh, our system, when it sees a query Adidas shoes men 15, because of the tokenizer that we are using, like it kind of drops 15. So the items that we are bringing in, they have Adidas shoes and men in the query, but it doesn't pay attention to the size. So as we saw in the human annotated examples, like this is considered irrelevant. And maybe like let's look at the final one, like just for men. So we see like some scented candles, a lot of scented candles. We see Bluetooth beanies, um, a lot of scented candles. And why are they coming here? Because like in the token they have like gifts for men. So we have items that are coming in because they have the term gifts for men. So we don't necessarily see like any unique possible gift ideas. So this is an interesting data set. If you want to play with the baseline, take a look here. We'll look at how to kind of improve, or how we can kind of improve this kind of relevancy gap here. Like for example, we are we're bringing in like kind of relevant items, but we're not paying attention to size. So we'll see how we can use LLMs to help improve that. Yeah. So the takeaways, from the end of this section, like I hope kind of saw how like a simple token-based retrieval can work, how it might suffer from things like keyword stuffing, like for the gifts for men, the items that are coming on because the item has those tokens. Um, depending on your tokenizer, you might drop some tokens that might be important, like, if you have a specific shoe size that you're looking for and it's not paying attention to it, um, the item that you might get might be irrelevant for you. So this is the end of like, section one, kind of just showcasing what the problem is. Before we kind of go to the next section of like kind of getting an intro to LLMs, like maybe let me just see if there are any questions. Um, okay, cool. I don't see anything in the chat, so hopefully, yeah, hopefully the first section that we went over was clear. So let me go over the next section. So, like in this section, we can't really cover everything about LLMs. So this section, we're just going to be covering over some very high level milestones and just like some high level brush of some of the core concepts. So what is an LLM? I would say, an LLM is a large language model, like a neural network or a transformer network that that has maybe like a billion plus parameters. It's trained on a very large corpus, and because it's trained on a large corpus and also trained on like many different tasks, it can be used, like a single model can perform like a variety of creative things. So you can use that model for like chatbots, a model for like generating text, a model for like generating resumes, so like generating code and whatnot, translating languages, being like a yeah, helping you edit like some drafts of like something creative or whatnot. So this image is a bit small, but I just kind of wanted to compress all the maybe semi-big milestones that happened recently in the LLM space. I would say like maybe the first model that maybe in today's standard might not be considered a large language model, but maybe kind of set the space was BERT in 2018 from Google. So that was the first model that had like several hundred million parameters. So in this case, 340 million parameters for the large. Uh, there are many different variants of BERT, but this is for a large parameter, the large version of it. So BERT is an encoder, which it's been used for like you give it some text and then you use it like for classification or like getting embeddings or whatnot. So it's not like the generative thing that people are kind of using today. Then the next big milestone was 2019, where there was a network P5. So maybe the image might be too small, but basically you had one network that can generate like 4 or 5 different tasks, whether it's like translation, judging if something is relevant or not, summarization. You have like one model that can do either of those tasks. And that was about 770 million parameters. So in 2020, OpenAI released GPT-3, but that is an example of like a generative model, right? Where you're giving it some text and it can generate text. And that model was about like 175 billion parameters. And then, everyone is aware of like what happened last year. That's when ChatGPT, with like GPT 3.5 kind of came out. And partially because of how accessible it was and the performance of the network, like that's when I would say like the space kind of hit the popular, um, uh, yeah, hit the popular sphere. So in 2023 of this year, OpenAI released GPT-4 that fixed some of the problems that were there with some of the LLMs, things like hallucination or some of the problems, other problems, and it's the quality of this model is also much better. Google released their Palm 2 model in May of 2023. And just recently, a couple of days ago, they released their new Gemini model, which supposedly is beating GPT-4. So GPT-4, Google Palm, they're like private models, but there actually been a lot of research and development with open source models too. So in July of this year, Meta released several of their Llama models, 7 billion, 13 billion, and 70 billion models, which are all open source that you could use. So, we talked about these LLMs. So how do these LLMs perform some of these tasks, right? How do you train such a network? So I would say there's about maybe 3 stages. One is the pre-training stage. So these models need a lot of data. So thankfully, you have the internet and you can actually train it in an unsupervised manner. So we're talking about like a trillion words, trillion tokens. So what is the task that they're training on? And again, it's in an unsupervised manner where they're basically doing like text completion. So, my llama 8 plus, right? So you look at all the sentences of the internet, and then you're trying to just predict the next token that might be appearing. So this is pre-training. It appears in an unsupervised manner. You can train it on a very large set of data. The next task is supervised fine-tuning. So this is where you kind of need labeled examples. So at least 50,000 minimum, um, of where you have like some instruction, you have some input and expected output. So here the instruction is write a poem about llamas, right? And then you have like uh, uh, a pair of output that you want the model to kind of learn to predict. So this is like again like in a semi-supervised manner. Again, the model is just trying to learn to predict the tokens from kind of labeled examples. The final step, which is what kind of is critical to these chat models performing really well, is reinforcement learning, where you're basically asking the model to kind of generate, like here we're generating 3 outputs, and then a human is kind of rating like, okay, this output is relevant or not, and then you like tell the model to learn to rank and reprioritize its output to generate the one that was relevant. So this reinforcement learning is what was missing and what kind of gave some of the rise to some of the I say power of relevance of the newer models. So one aspect about the data is that these are data sets that are used in like Facebook's Llama model. So Common Crawl is like a data set of an open source initiative to crawl the internet, and it's about 3 terabytes of data. C4 is like a much cleaner version of the Common Crawl. Llama was trained on GitHub, Wikipedia, Stack Exchange. Books is like a mixture of like I think like 100K kind of books. Some of them are copyrighted, so that data set is no longer available. But the basic idea is you can see it's like several terabytes of data that it's trained on. And if you notice also here, it's because of the size of the data set, the model only goes through the data set not even one time, right? So it goes through Wikipedia like 2 times, but for other data sets, it's only like a factor of 1. And like from an architecture perspective, the one that kind of led to this evolution was the transformer architecture, and attention is all you need. So transformer is composed both like an encoder and decoder. So BERT is an encoder, but all the generative AI kind of piece that we're seeing together is powered by decoder. And um, as you see, like more, these days, many people are just stacking more and more of these architectures. So, like BERT a couple of years ago was like 300 million parameters, but now like we're on several billion parameters. So with such large networks, with such large data set, which like efficient GPU compute, we're able to train these networks. Okay, so we're training these large networks or making these networks larger and larger. So how do you evaluate a network? Like, so there are many models. Do you use OpenAI's GPT-4, or do you use Google's Palm or Gemini, or do you use Llama? How do you determine which model to use? So there is a leaderboard, the chatbot arena leaderboard that you can click and visit. And there are a couple of metrics that they have. The metric that I'm most interested in is this arena ELO rating. So basically, what you have is like you have some prompts, you send it to like two models, and then you ask the human to rate whether the output of one of these models is more relevant or much better. So um, it may not be a surprise, but like the models that take the top spot are like these proprietary models, from OpenAI and like Anthropic. So they have a pretty high ELO score, like kind of like a chess kind of rating. But if you look a little bit late, sorry, I do hide some of the entries in this dashboard to kind of emphasize some models. So if you see here, we have Llama 2, 70 billion parameters, which is an open source model, and it's getting a pretty high ELO rating. And so the Sapphire 7 billion model, so this is 7 billion, it's a factor of 10 smaller. It's also getting a pretty decent score of 1042. So Facebook kind of released their 70 billion model, 7 billion, and 13B. So you see like the 7B and 13B have like 1021, but the Sapphire model, which is just 7 billion, has a score of like 1042. And just because a model is proprietary doesn't mean that it might do better than open source models. So this is the model from Google, where based on this rating, it performs a little bit worse than some of the top models. So we covered a lot with LLMs here. So this kind of just gives like a very broad brush of the space. Obviously, there's a lot of details that are not covered, but in the labs, we'll kind of see like how the output of this LLMs actually, yeah, the output of these results for the problems that we have in the e-commerce space. Before I go to the next section, let me see if there's any quick question. Okay, so Hipern has a question about Elasticsearch. Um, um, yeah, so so Elasticsearch, it's a full text search engine system. It supports both text search, and now it supports vector search. In the notebook that we saw here, so like in this notebook, I do have like ground truth labels. So for query items, so this is like this shows whether a human annotator found something relevant. For just a simple baseline, I do have this relevance here just to show, like, are we bringing in items that are considered relevant or not? So um, probably for most of these examples that we bring, we are probably bringing in items that are different from what Amazon's production system brought in. So most of it will be unlabeled. Yeah, yeah. So sorry for the possible confusion there. Cool. So we don't have a notebook for this thing. It'll be combined in the next section. So let me just quickly go to section. So the prompting section. So yeah, so this section will be short, and then we'll have several notebooks related to interacting with our LLMs. So let me go here. So how do you talk to these large language models? They're trained on English data sets. I mean, they're trained on like text instructions, so you can talk to it basically like in plain text. Um, and the beauty of this is, um, uh, if you're detailed in your instructions, you can get it to output like powerful powerful results. So let's consider, but there's still some kind of small art in kind of generating like a valid kind of set of instructions. So in a prompt, I would say there's maybe like 4 pieces. So one is like you kind of give the role. So um, if you if you're looking for like the output to be generated in a certain tone, or like the model to consider certain domain knowledge, like if you have like a role as kind of like your first prefix of your prompt, the model might acknowledge that and kind of like output results in a relevant tone. Then you have the typical instructions. Again, the role is optional though. Most people might just start with instructions here. So here, the sample prompt, we have classified below medical news as healthy or concerning. So then we have some input text, the some medical text here, and then you have output. And the output here is what you want the model to generate. Sorry. Sometimes, depending on the type of problem, you might want to give your model some examples. Like if you want it to return in a certain way, or a certain output format, or you want it to maybe give an explanation in a certain tone or a certain manner, you can provide like input output pairs. So in this example here, we have 2 input output pairs, and then we have our final example where we want the model to generate an example. The other kind of prompting thing is, the model is kind of trained to generate the next token, but maybe because of that, it might sometimes be greedy, and it might generate a token that might not be completely valid. So this is like a reasoning exercise here. So if we take a look at this example, we have a juggler can juggle 16 balls, and half of the balls are golf balls, and half of those golf balls are blue. And the question is, how many blue golf balls are there? So we have 16 balls, half of them are golf balls. So we have 8 golf balls, and we know half of those 8 are blue. So that means we have four um, we have four ball we have 4 golf balls that are blue. But the model, maybe because it didn't necessarily pay attention to part of the context, it greedily answered 8. So sometimes, depending on your task, you could add things like, explain your reasoning, or let's think step by step, or whatnot. And this will just allow the model to kind of um, reason a little bit better before it kind of outputs an explanation. We won't really cover too much here, but there are some parameters that you can use to control the the output of a prompt. So all the models have these kind of common parameters about like whether to kind of greedily choose the most relevant token, or to sample from only the top relevant tokens, stuff like that. We won't really be playing with these parameters directly in the lab, but it's just something to think about depending on your task, whether you want it to kind of do it, whether you want it to be like a co-pilot in like a creative task, or kind of more like a structured, rigid task. So we have 3 notebooks here. I will be covering one of the notebooks, and then my colleague, Mr. Erb, will cover the other 2. let me share my screen. Let me go to the next notebook. So we have 3 prompting notebooks. Actually, maybe 4. Sorry, we have like an intro prompting notebook, which I'll be covering, where we'll be showing how you can use something like LangChain to um, talk to different LLM providers, and we'll also see some of the examples of like zero shot and few shot. So let me let me just run this again. So I do have some of the LLM outputs cached. So when we run this notebook, it'll just be a little bit faster, and the cache is also saved inside the repo. So if you decide to run this notebook externally, because there's the cache, you don't necessarily need to like create an API key with all these different vendors. So the first use case that we'll be covering is just like a reasoning task. And let's start with like, kind of the best model out there, which is OpenAI's GPT-4. So GPT-4 supports like different context lengths. So we're just using the default, which supports like an input length of 8,000. For the use case that we have here, we are not providing like very, very large inputs. So we'll just stick with the default for today. So I have a template here where I'm going to ask a question. I'm going to provide this as a variable, and then I expect the model to generate an answer. So again, I'm just going to cover, this is heavily using LangChain, partially because of its caching, and then partially because I think it makes it easier to interact with different LLM vendors. So here's just a template, a string. We have these variables here. I have an input variable question. So let me, and I have this question, can Barack Obama have a conversation with George Washington? If I use like LangChain's prompt to format it automatically replaces the question here. And yeah, so we initialize the LangChain has a way of like sequencing, different chains or different sequence of activities. But in our case today, we are just going to be prompting the model directly. We won't be doing any fancy stuff. So, so when I make a call to the model to run something, like I have this question here, the underlying library kind of adds this like role here, like, okay, it's the human that's asking this question. And let's see what it generated here. So, okay, so here we see that, there was about 22 tokens in the input, and there were about 23 output tokens that were generated. And it costs about like 0.02 cents. So, and this is the response that came from the LLM. No, it's not possible because George Washington passed in a certain age. Yep. So this is the output from GPT-4. You can make a prompt request to the OpenAI API and kind of figure out how much tokens are there, or the tokenizer that is used by OpenAI is available. So, for this query here, we see like this is how the input was tokenized. Yeah, and so you can do a count there. So we saw the response from OpenAI. So let's look at the response from another proprietary model. So this is Google's Palm model. So it does seem to take some time. So let's just look at the response that we already pre-generated. So the response did come. So it gives like the correct answer. It's not possible. Again, same thing like ChatGPT, because it considers when the person died and was born. But then kind of like, I wouldn't say this as hallucination, but it kind of gets into some creative answer. Like Barack Obama can have a digital conversation. A conversation with a digital representation of Washington, and with text to speech and whatnot, you can kind of do something realistic. So it kind of goes into some of the creative aspect of the answer. And then like Barack Obama can have a conversation with mediums such as Ouija board or seance. So it does, I wouldn't say it's hallucination, it does get into like some creative response here. So let's look at the Zephyr model. This is the 7 billion model, which is open source. So yeah, so here we're using Hugging Face Hub. So Hugging Face, so the model is in Hugging Face, and Hugging Face kind of provides like a free endpoint to kind of run some things. So the inference is not running locally. But from LangChain, if you wanted, you can, assuming you have all the dependencies and the infra, you can use like Hugging Face pipelines to kind of run the inference locally. So it does take some time here. So again, because it might be like scaling up dynamically for the request. Maybe while this is running, maybe we'll just wait a couple of seconds here. So again, this is like the open source model that was trained by Hugging Face, and it's only 7 billion parameters. So the response we get, no, Barack Obama cannot have a conversation. Conversations can only happen between living beings. So I would say like OpenAI and Zephyr kind of provided the most correct response. Like Google's Palm was being maybe a bit too creative, and maybe that might be like those default parameters with like temperature and whatnot that Google exposes. So running Llama can be a little bit expensive, or it might be a little bit difficult locally. We may need like GPUs and whatnot. But I found this serverless provider for like for making requests, ad hoc requests to some of the Llama models. So Facebook released like three parameter sizes, 7 billion, 13 billion, and 70 billion. And then they released like the base model and then like the instruction tuned versions of those models. So let's see how these models perform for the same request. So I'm just, maybe in the interest of time, I'm just going to show the output here. So for this prompt here, like we see the output is like it's returning a list, strong no, strong yes. So it returned 2 answers. So yes, if you're talking to an actual person, but then yes, it's possible if you're talking about like like a founding father kind of stuff. So I think this answer kind of hallucinated a little bit. Like I'm not sold by this explanation here. So this is the 7 billion base model. The chat model, it's like, okay, this is an interesting hypothesis. Okay, but in the end, it kind of gives a relevant answer. But you see, like already with like, it didn't directly answer the question, right? It answers, okay, yeah, they're born in different time zones, but we kind of stopped it early. Like it's just kind of talking a little bit. Yeah, so this was the 7 billion model. So let's look at the 13 billion model. The 13 billion model, it responded kind of quickly. No, they both lived at different times. The chat-based model, again, like it's kind of hypothesizing a little bit and kind of coming up with some slightly different response here. So yeah, maybe in the interest. So this is the 70 billion model. Let's look at the 70 billion chat model. So again, we see the chat model is kind of rambling a little bit and not, maybe not giving the answer in the shortest, cleanest way, like as OpenAI and Zephyr. So this is like kind of the reasoning case. Let's actually look at the like the subject for this case, the e-commerce use case here. So the examples that we'll be looking here is kind of dealing with like the vocabulary gap problem. So the idea is, you have maybe like an item title, but it doesn't have tokens that a user might be searching for. So can we use a large language model to generate queries that a user might be searching for if they came to this item? So let's just set debugging false, and then so the use case again is given an item title. We want to generate queries that a user might search for. So the sample item title that we'll be playing with is this biodegradable bamboo, natural charcoal toothbrush, eco-friendly, sustainable. It's definitely like a stuffing of words here. So let's see let's see how it performs with just zero-shot prompting. So here, we just provide a use case. We don't provide any examples, and let's see how it performs. So again, so this is the prompt. You're given a title, generate 2 possible search queries, and this is the response that we get from OpenAI, which I think is pretty good. Eco-friendly toothbrushes, pack of 6, and 2 composable travel toothbrushes with soft bristles. So this response is relevant, but if you notice, like this output is just like a string, and there's 1 and 2. It's not like a way that is easily parsable. So what we're going to do in the prompt is like we're going to tell it we want the response to be generated as like a comma separated list. So again, LangTail kind of makes it easy. We have a regular prompt template, we have our input variables, and we can provide like instructions here. So let's just run this here and just look at the prompt. So we added format instructions here. LangChain has like some automatic instructions that it adds here. So it says your response should be a list of comma separated values. So we do the same prompt here, but then we also send the response to the parser. So at first glance, it kind of looks right, but if you notice, like we do have partially invalid tokens. I mean, partially invalid output. So here, like we have it in strings, but then we have like a quote here and a quote here. So the model didn't really generate the output in the correct manner. So to kind of help this thing here a little bit, I noticed that if I just say like, hey, you're an e-commerce shopping assistant, and I do the same prompt, just adding this line, it generates the output in a much easily parsable manner. But I think in general, like when you prompt and like you want outputs for kind of like your system or for your use case, it's good to always provide some examples. So here, we have our role, we have our prompt, and then we have some examples. So I say like, oh, here's this, Pokemon special complete edition, sorry. And then we have like 2 queries that we generated from the logs. So this is based on the engagement data that we saw from the data that Amazon has. But you could also come up with your own queries. So here I'm just providing 2 examples, and then I'm running the same prompt again. And again, I would expect the same results, right? But it's just much easier to parse. So this is like with OpenAI's model. So let's look at the open source model from Facebook, the Llama model. So one thing is the Llama model, the prompt is a little bit different. So what you need to do is like you have an instruction here, like you need to have the instruction tag, then you have the system prompt, you have the user message, and then the end of the instruction tag. So if we take our existing prompt, like so we have the system prompt, your e-commerce shopping assistant listed here. Then we have this whole thing is like the user message here. So yeah, I'm running maybe a bit short on time. So let me just look at the rendered output here. So so let's look at the results. So this is using the Llama 7 billion model. So the prompt here. So we see it's just kind of generating like some code, is not relevant at all. If I look at the 7 billion chat model, like it's not generating, like it's generating queries for the sample I provided, not for the one that I wanted to provide. So 7 billion is pretty small, I guess. But if I use, yep, so it's not working. So the 13 billion model, again, I've noticed like the regular non-chat-based models, they just kind of seem to want to generate code. The 13 billion chat model, we are starting to get relevant stuff. So it says, it kind of gives a verbose response, but it does generate like eco-friendly toothbrush, travel toothbrush. If we look at, again, the 70 billion model, not the chat-based model, but we see that it, again, is not generating code, but it's not really relevant here. But the 70 billion chat model, it generates queries that are relevant and also gives an explanation about why the item might be relevant. So, yeah, so maybe for the final thing, I wanted to show like the open source models. Zephyr, again, this is 7 billion. And the same prompt, and these are the queries that it gave. So it gave the queries and it gave its explanation. So this 7 billion model, open source model, is doing better than like the Llama 7 billion and the Llama 13 billion model. So just sorry, we covered a lot here. So just the takeaway from this notebook is LangChain kind of makes it very easy to interact with different LLM options there. We kind of see that LLMs are pretty good with reasoning. Definitely, GPT-4 is like if you're okay with paying the cost, it seems to perform the best. If you want the output in a certain format, like doing few-shot prompting is important, and even like smaller models, 7 billion model, can perform well. So this is the first notebook that we have in prompting. Now, my colleague Mustafa will be showing how using prompting we can solve like two other cases that we talked about. So let me stop sharing and give it to him.
Hi everyone. So in this notebook, I will talk about how we are using the large language models to understand the queries and the products. So in previous notebooks, Nidin talked about a simple token matching search system. Like think about a BM25 model that uses a like bag of words logic, tries to match the tokens of the query to a tokens extracted from an item, uh, and scores these token matches and ranks the items by some way. But notice that it doesn't pay attention to the attributes or the meaning of the query or the attributes of the item at all. So it's basically just a token match and scoring those the matches with some weighting, and it ranks the items. But assume that you have a system that you can actually understand your items, extract your attributes of those items, and uh, and index them somehow. And when your query comes to your system, you also extract the attribute of the query and try to match in a smarter way. So I will show in this notebook how we can do it with an with LLM with prompting. So let's just sure let's get it done. Um, yeah, holding environment and everything. So this is basically just in an e-commerce setting. We are in this part. We are trying to set. We are only going to check a couple of attributes of the products for this notebook only. In a general use case in e-commerce, they're definitely looking for more than 4 or 5 attributes. But for this notebook only, we'll check a couple of them, like product type, brand, gender, color, and size. So this is just for output formatting. I'll just gonna skip this fast. Um, so let's look at the prompt. Okay. Uh, so this is a few shot prompt. Okay. In a few shot prompt, most of you know you'll provide some examples to LLM and to help the LLM put in a state that it can extract extract the attributes in a better way. So in a general way, we use you are an e-commerce expert. Your task is to extract attributes from a customer query, and possible attributes are product type, brand, gender, color, and size. Okay, then we provide the examples here. So the first example is yellow 35-inch baseball bat. So we say there's no brand in this query, there is no gender in this query. The product type of this query is baseball bats. That means the customer is only looking for baseball bats. The color is black and size is 35-inch. And the second example is some kind of men's waterproof ski jacket. And we extract another brand, gender, product type, color, size. We say none for them, and we provide the code as an input here, and some other formatting instructions are there. So in let's run this. Let's first format our query. So this is going to be our prompt for the Nike men's shoes. We will expect LM to generate an output, and the output is going to be in this format. So let's do that. Let's actually make this first Nike men's shoes. So as you see, the LLM can extract the brand as Nike, gender as male, product type as shoes, color green, and there's no size intent in it. So we can do the same thing for this is for query only. We can do the same thing for the product type products. So as you see, the LLM generated the brand as Mordang, gender is male. I noticed that the LM generalized the man to a male by using the dictionary that we provided there. And the product type is a ski jacket. There's no color intent, and then there's no size in it. So uh, so think of this way. So your index is most likely is going to be static or is going to change very minimally. You can update it in every couple of hours or a couple of days, depending on the scale of your system. So you can extract your attributes in some way by using LLMs. And when the query comes, you try to match in a smart way to the items. So this is one use case that you can solve the token matching, uh, going from token matching to understanding the query, and you can improve your system in some way. The one other notebook I will present in here is going to be understanding the relevancy of the query to an items. So if you're a search system, what you want to do is most of the time you want to understand how your system is doing. Like when you present a query, or change your algorithm, how is your system is changing. So usually, what is done right now is, or what is done in a couple of years back is, some queries are selected from the systems, and some items are extracted by using these queries, and the manual annotators are going over these query item pairs manually and scoring them as a relevant, non-relevant, or they can use some ranking scale from 1 to 5 depending on the system, like 0 as non-relevant or 1 as somewhat relevant, 2, 3, 4, 5. 5 is perfect maybe. But right now we can use LLMs to generate that data. Let me do this in this one. Okay, problem in here. Anyway, I already generated some of them before. So let's see a couple of prompts in here. This is a zero-shot prompt. I do not show any example to the system. What we are saying is this: you are a helpful e-commerce assistant, and you will judge relevancy of an item to a query and respond in one of the 3 options below. So we are only providing 3 options to LLM to judge the relevancy of the item to a given query. We are saying the first one is relevant, if the item is relevant to the query. Second, partial relevant if the item is somewhat relevant to the query, and irrelevant if the item is not relevant to the query. And in a one-shot example, we are helping the LLM by providing an example. The example query in here is we're saying 30 ounce tumbler with a handle, and one-shot item is some 30 ounce tumbler with a handle, some extra tokens there. And we are providing the query and item description. We are asking the GPT-4 to judge the relevancy of item to the query. So let's see the first example. We ask Adidas men's shoes size 15, and the item is actually contains those tokens as well. Adidas shoes with size 15 and some extra tokens there. And the LLM answers as a relevant, but notice we also ask the reasoning of why you're answering it as a relevant, okay? So the LLM answers in this way. The, the LLM finds the size intent in it by size 15, the brand is matching, and the gender of the item is also matching to the query. So it is answering it as a relevant. And we are changing the item this time. We are asking same query with a different size, okay? This time LLM answers it as a partial relevant because it thinks that the size difference can be a partial relevance. We saw in the previous example in the manual annotators, Amazon manual annotators mark them as non-relevant, but LLM answers as a partial relevant. So we will show like the fine tuning of the LLMs. So you can somehow use this manual data to fine tune your model to make your model to answer instead of partial relevant. You can make it as you can make it answer as a non-relevant. It's we will explain that in the one more in another notebook. So the other example is. This is a non-relevant example. The item, we changed item completely right now. It is a hiking boots for women and size 9. And this time, LLM answers as irrelevant, and it explains the reasoning because the brand is not matching, the gender is not matching, and the size is not matching. So it's an irrelevant item. So we can do a harder example. These three was kind of easy. We can ask gifts for men. So think about the system when you provide a gifts or man to your system in a token match sense. Okay, it's so hard to come up with examples or results there because it will only try to match gifts and man tokens in your system. So in this time, when we give the gifts for men and the item to the LLM, so the item is the metal hiking boots for women and size 9, and it answers are irrelevant because the reasoning explains by itself. Actually, it says that it's a pair of women's hiking boots, and it's not relevant to user query. The second example is the same query again. We are providing the item as virus control for PlayStation 4. And LLM's reasoning is relevant, and it says this can be a decent present gift for a man. And the one last example was we are providing a PAT insulin syringes. This is completely irrelevant, and LLM answers as irrelevant and provides this as irrelevant, and it provides its reasoning as a why it's an irrelevant item. So one use case of this relevancy judgment can be evaluation. This is very useful. You can save lots of cost by skipping the manual labor, and it's also very it's going to reduce the timing because when human annotators are work on these tasks, it takes lots of time for them to generate answers. The third one is scale. You can judge lots of queries and lots of items by this way. And one other use case can be you can use this kind of data for learning to rank. So when you can generate this kind of relevancy information, you can use these kind of relevancy pairs, query item pairs, to train your re-rank models and make your system better. I'll go back to the slides. So in this part, I'll talk about how to fine tune the LLM models. So, so we have now LLM models out there. They can do many tasks in a great way. But uh, think of a use case that you want to make it special for your use case. Okay. Um, so if you want to if you need a model, you can train your model by ground up. That will take lots of time, and you will spend lots of money on it. So in order to skip this step, you can fine tune this model with a very small data set, relatively small data set compared to original data sets that's provided to this that are trained to big LM models. And this model can also better perform better than the generic LLM models. Um, and also it can use the LLM's learnings or its knowledge in the its weights to generalize your task better, um, and transfer the knowledge that it already contains to your task. Um, and you will not have much of a privacy concerns, and you will also own the IP of the fine-tuned model. So, what kind of problems you may have faced with when you're fine tuning? So, one of the biggest problem is the data collection. And the quality of the data. You need to provide a good quality and some good quality data to get a decent LLM model. And one other problem is overfitting and catastrophic forgetting. This happens when you train your models when you overtrain your model and somehow your model weights are updated in a way that the knowledge that it already contains in the base model changed, and your model is not able to do generalization anymore. And because it fits to your data that you provided a lot, um, then you lose most of the capabilities of LLM at that point. The other problem is the computational resources, because these are very big models. They need lots of GPU and computing power. Um, uh, so even for fine tuning, you might face these kind of problems. Um, Also, the other problems can be lack of interoperability. This is actually very big problems for the generic neural network models, but uh, you may face with these kind of problems as well. Um, and lastly, these LLM models are instruction tuned. So when you train your model in a way, if your input data is not set in a good way, you will have problems with instruction tuning as well. So let's think about a relatively small LLM model, 7 billion parameters. A 7 billion parameter LLM model will think about 2 bytes of per parameter for the weights, or 4 bytes per parameter for optimizer state, 2 bytes per parameter for gradients. And in total, you will need 52 gigabytes of memory to just to fine tune your model. And we ignored some of the other things like batch size, sequence length, and others. So, in order to solve these problems, a couple of years ago, these smart men on the top right, they introduced the LoRa, low rank adaptation for LMs. What is happening in LoRa is they freeze the pre-trained model weights and they inject some trainable rank matrices. So think of LLM as a big matrix that is D by D. Okay, I'm simplifying everything here. So and what they did was they just partitioned this to the smaller matrices that are trainable, and they trained these matrices instead of updating the whole weights of the LLM. So think about this W as frozen weights, uh, and only these smaller matrices are trained. So some let me show Laura's performance in some of the tasks. They're directly taken from the paper. GPT-2, the GPT-2 medium, fully fine tuned without LoRa. Okay, it fine tunes over 300 million parameters. And with LoRa, this number of parameters dropped to 0.35 million. In this, just check the blue score. Its score is better than the fully fine-tuned model. And you can check the fully fine-tuned in GPT-2 large as well. The blue score is, again, it's this better one, better than the fully fine-tuned version of it. So what is found is mostly with LoRa, you can at least get performance on par with fully fine-tuned models. So one of the target parameters of LoRa is the rank parameter. So improving the rank, increasing the rank parameter will have benefits in the performance of your fine-tuned model, but this improvement plateaus after some level. And for some data sets, lower rank also performs better. There's a new other version of the LoRa that is a quantized LoRa. In this version, the improvement is done on the memory requirements. In quantized LoRa, quantization is done on 4-bit normal float precision. And one other benefit of QLoRa is they use double quantization that saves further. It's like quantization of the quantization, actually. It saves like 0.337 bits per parameter. They also introduced like page optimizers to prevent some memory spikes. And QLoRa lets you train your fine-tune your model with less hardware requirements. So how you shape your data for fine-tuning? So think of your system as, again, you want to fine-tune an instructive way. So you provide your data in a shape of prompts. You provide your question and the answer. You can say in a question answer. So let's say if you are fine-tuning our model to just predict the product type of a query, your input is classify product type of this query. You provide your query and you provide answer, and you let your LLM to predict and compare your answer to the label and do all this gradient descent, etc. For the lab, Nadine is going to continue with fine-tuning example.
Yes, so we're running a little bit low on time, so maybe I'll just share the results and then kind of go over the very few remaining slides. Um, so I just wanted to show the results for, for this query, Nike black men's shoes. If we use the, attribute extraction case that Mustafa mentioned, we do get product type shoes, brand Nike, all that. So with GPT-4, it kind of works well. And if we just do like the llama base model, or the llama base model, it generates some stuff, but then it generates like other kind of irrelevant tasks. So what we did is like we just fine-tuned a model like on the instruction pairs that Mustafa shared, but we used like GPT-4 to generate the training data. And then we kind of send the same query, and this is the output from our fine-tuned Llama 7B model. Yeah, so let me just go to the 3 slides to kind of tie like some final things together, and then if there are any questions. So, we covered a lot. So I just want to kind of tie some of the things that we mentioned. A user comes to like an e-commerce site, they have a query, like gifts for men. It kind of might be ambiguous. So you might have like an LLM or some type of model to kind of help rewrite it to extract the queries in a more understandable manner, right? And then you might have like the attribute LLM kind of model to extract the intents of the query. The same model you might be running on the items side here. And then, you can use your Elasticsearch, the full text search or vector search or whatnot to kind of retrieve these candidates. So the model that kind of extracts intents, you kind of annotate your items with those intents too. So then you can use Elasticsearch, kind of like matching on product type or whatnot, or whichever system. So you kind of get all these candidates, and then you can kind of use an LLM to kind of uh, see if something is relevant or not. So here we use LLMs kind of for all these kind of four use cases, but you can also use LLMs for training data and then train much cheaper model. So I just wanted to share like other places where this kind of architecture or where LLMs are being used in the e-commerce scenario. So Shopify, I think like a couple of weeks ago, they had a blog post about how they allow their merchants to kind of generate product descriptions or based on like some keywords that they generate that the merchant puts in their form, and then it uses some large language model to kind of generate product descriptions. Um, we talked about this ambiguous query. So from Instacart, if you have something like what pairs well with salmon, like in the first image you have like things that have like salmon in the keyword, but that may not be kind of relevant. What pairs well with salmon is like seasoning, a lemon, or whatnot. So this is kind of where they're using an LLM to help extract the intent. I mean, help reformulate to understand the query and then show results for that. And this workshop was kind of inspired from a paper from Etsy, where they basically showed this use case of using Llama that they fine-tune on their corpus to kind of uh, extract a product type here, or to extract like what the user is searching for, or to extract rewriting the query. So this workshop was kind of inspired by this session from this paper from Etsy. So this is the last slide that we have, and I just kind of want to share the results from Etsy's paper here. So their instruction was, um, which category, I'm going to give you a query, which category is this query in? So the query is Himalayan salt lamp, and the correct answer is home and living. So GPT 3.5, it has its own kind of taxonomy understanding. So it said home and living. So the Llama 7B, which you know, this is not fine tuned. You see, it's kind of very verbose. It's kind of giving like it's giving not just the answer, it's giving some other stuff. The 30B parameter model gives the correct answer, but it doesn't match the casing of internally Etsy's taxonomy. But the fine-tuned model that Etsy did, even the 7B, kind of uh, gave it in the format that Etsy was looking for. So this is kind of the last slide that we had here. So sorry, there was a lot of material here, but I just wanted to show, um, like in an e-commerce scenario, there's at least a couple of problems, like understanding the query, ambiguous queries, understanding the intent of the items, relevancy, and just show how you can use something like LLMs to kind of help tackle these problems without, training like any expensive models or whatnot. Yeah, so that was the last slide that me and Mr. Barrett. Let me see if there are any questions. Um, I would say like this is an example of like retrieval augmented generation. So you have like a query, you're using like a LLM to kind of rewrite the intent, and then you can kind of go through the normal kind of search flow. Like, you could just rewrite the query and then directly use Elasticsearch or whatnot. Or you can kind of use LLMs and kind of help solve these problems. Uh, I think like in a production system, because latency is kind of a concern, like it's very expensive to use like LLMs in for solving all these problems. In our case, like we use like caching, so that's why it seemed like the response came pretty quickly. Otherwise, like GPT-4 or whatnot could take like a second or so. Yeah, so which could be expensive to run real time. And the slides are in our repos, so if you want to, and we also have a contact info in the first few slides. So, please feel free to reach out. Cool. Thank you.